Good day students. Welcome to our second video lecture in system software. So in our last class we have seen about the introduction to system software and about SIC architecture. So today we are going to see about SIC XC architecture. SIC comes in two versions, SIC basic model and SIC XC extra equipment. So SIC XC is our upward compatibility model of our SIC architecture. SIC stands for Simplified Instructional Computers that we have seen already in our last class. All the hardware features that we have seen in our SIC comes with SIC XC also, because SIC XC is the upward compatibility model of our SIC architecture. So in all the architectures we are going to see only about the 6 hardware features commonly. So the first hardware feature is SIC. In SIC XC is memory. So in SIC XC we have maximum memory. So the memory is about 1 MB, that is 2 power 20 bytes, whereas in SIC we have 2 power 15 bytes. This increased memory level leads to change in addressing modes, instruction formats and everything. The next hardware feature is registers. In SIC we have seen 5 registers: accumulator register A, index register X, linkage register L, program counter register PZ and status word register SW. Along with these 5 registers, in SIC XC we have 4 more registers: B, S, T and F. So all usually in our computer machines, each and every registers will be represented by a number. So each and every registers will have a number. In SIC we have seen that the number for accumulator is 0 and for index register is 1 and so forth. So likewise in SIC XC these 4 registers also have certain numbers. So the number for B is 3 and the number for S is 4, the number for T is 5 and the number for F is 6. So B is nothing but our base register. This is used for addressing, and S is general working register, no special use, and T is also general working register, and F is floating point accumulator. So these are the 4 registers, additional registers available in SIC XC. So we have already seen that in SIC we don't have any floating point hardware, so floating point numbers are not supported by SIC machine. Since floating point hardware is available in SIC XC, SIC XC will support floating point numbers. Next, data formats. So data format is same as SIC. Since we are having floating point hardware, so there are special formats for SIC XC to support floating point numbers. The format is, this is the format, this is the instruction layout. S, exponent and fraction. S is 1 bit and exponent is 11 bits and fraction is 36 bit. So SIC XC support 48 bit, in total 48 bit floating point data type, 48 bit floating point data type. So the fraction value is between 0 and 1. Fraction value is between 0 and 1, that is assumed binary point is immediately before the higher order bit. For normalized floating point numbers, higher order bit of the fraction must be 1. Then exponent. Exponent is an unsigned binary number and its value is between 0 and 2047. The absolute value of a number is represented by this formula, f into 2 power e minus 1024. Here E stands for exponent and F stands for fraction value. Then the sign of a floating point number is represented by S. So if the value of S is 0, then it is a positive number, and if the value of S is equal to 1, then it is a negative number. 0. How the number 0 is represented? So the number 0 is represented by setting all S, exponent and fraction bits to 0. So this is about data formats. Next hardware feature is instruction formats. So the instruction format of SIC architecture is simply opcode X and displacement address. So this is the instruction format of SIC architecture, whereas in SIC XC architecture we are having 4 different formats. Let us see one by one. Format 1. So format 1 is of 1 byte, that is equal to 8 bits. So format 1 represents only the opcode, that is opcode is represented in 8 bits. See, opcode is nothing but each and every mnemonics we are having a opcode. For example, let us take an instruction or sub. Or sub is nothing but returns to a subwritten. The opcode for or sub is 4C. So this is predefined. For each and every operation we are having an opcode, the number, that is the number representation of a instruction. Okay, mnemonic instruction. So the opcode for or sub is 4C. So we have to write this 4C in 8 bits. How we will write 4? 4 is written as 0100 and C is written as 1100. So this is 4C. So this type of instruction layout comes under format 1. Next, format 2. Format 2 is 2 bytes. So format 1 is 1 byte, format 2 is 2 bytes, that is equal to 16 bits. So in format 1 we have represented only the opcode. In format 2, this is the instruction layout of format 2, opcode R1 and R2. It is specially used for register to register transmission. So opcode is represented by 8 bits and register 1 and register 1 in 4 bits and register 2 in 4 bits. So this is the instruction layout of format 2. Now let us see an example. COMPR, compare AS. So this is our instruction. We are going to compare the values present in the registers A and S. As we have seen before, each and every register will hold a specified number. So the number for register A is 0 and the number for register S is 4. So we have to represent 0 and 4 in 4 bits, and the opcode for compare mnemonic is A0. So how we will write A is 1010, that is 10. 10 is represented as 1010, this is A, and 0 is represented as 0000 in 8 bits. Then register R1 is our A. So the number for A is 0, 00000. Then R2, the register R2 is S. So the number for S is 40100. So this is our final instruction layout. From this instruction layout, we can write the opcode. So opcode is equal to, you just combine all the numbers A004. So this particular instruction, compare A comma S, is stored in this format A004. So this is hexadecimal representation, but actually in memory it is stored like this in binary format: 1010 0000 0000 0100. So this is the actual opcode of this particular instruction. Since we cannot understand the binary representation, So in our complete syllabus, we will be going to represent the opcode in hexadecimal numbers, just for our understanding purpose. Next, format 3. Format 3 is 8 bytes, that is equal to 24 bits. Format 3 and format 4 are somewhat complex. In format 1, we have just seen about the opcode alone. In format 2, opcode and register 1 and register 2 operation. Whereas in format 3 and format 4, we will be representing all the different kinds of addressing modes that we are seeing in our architecture, in our instructions. So this is the instruction layout of format 3. Opcode N, I, X, B, P, E and displacement. So this is the instruction layout. Opcode is of 6 bits, N is 1 bit, I is 1 bit, X is 1 bit, B is 1 bit, P is 1 bit, E is 1 bit and displacement is 12 bits. Okay. So N stands for indirect addressing. I stands for immediate addressing. X stands for indexed addressing. B stands for base relative addressing. P stands for program counter relative addressing. And displacement is our address. Okay. So depending upon the addressing modes that we are using in our program, we will be representing each of this N, I, X, B, P, E value as either 1 or either 0 depending upon the addressing modes. So we will see in detail when we see about addressing modes. So let us see an example for format 3. LDA #3, load 3 into the accumulator. So this is the meaning of this mnemonical instruction. So always hash means immediate addressing. So if it is an immediate addressing, what we have to do means we have to put number 1 in the place of I. Okay. So the opcode for LDA is 00, and since it is an immediate addressing, we have to place 1 in place of I. Then 3 is the actual value. So this actual value is represented in displacement field, because we won't be involving any addressing and all. The value itself directly given in the instruction. So this value is directly written in displacement field. Now let us write this particular instruction in this instruction layout format. So first LDA, the value of LDA is 00. So opcode should be represented in 6 bits. So first 0, 0, 0, 0, 0. Next 0, 4, instead of 4 zeros, we have to take only 2 zeros. So 0, 0. Then since it is an immediate addressing, we have to write 1 in place of I. So I have written 1 in place of I. Remaining everything is 0. Then displacement. So as I told before, in displacement place, we have to keep this value as it is. So 3 is represented as 0, 1, 0, 0, 1, 1. So this is 3. Since we have to represent it in 12 bits, I am appending 2 zeros in the prefix. So this is the final instruction layout. Now let us see how we will write this instruction layout as an opcode. So I have to split it 4 digits. So this 4 digits 0 and this 4 digits 0, 0, 0, 1. What is the value? 1. And this 4 digits 0, 0, 0, 0, value is 0, and this is 0, 0, 0. So finally the opcode is 0, 1, 0, 0, 0, 3. So this is under format 3. Next, format 4. Format 4 is 4 bytes. That is equal to 32 bits. So the instruction layout for format 3 and format 4 are both same. except in 12 bits of displacement field we are having the address directly, so the address value is represented in 20 bits. In format 3 we will represent in 12 bits, in format 4 we will represent in 20 bits. Then if it is a format 3 instruction, the value of E is 0, and if it is a format 4 instruction, the value of E should be 1. This is the only difference between format 3 representation and format 4 representation. Now let us see the instruction layout of format 4. So the instruction layout is this one: opcode NIXBPE address, same as we have seen in format 3. Format 4 also have the same instruction layout, except the address field is 20 bits. So now let us see an example for format 4. Everything, opcode is 6 bits, NIXBPE or all 1 bits, and address is 20 bits. So this is the example for our format 4 instruction JSUB RD or EC. So jump to the subroutine present in the address 1036, that is RD or EC is a label. So this label is present in the address 1036. So we have to take this address field. Then JSUB, the opcode for JSUB is 4B. So from the instruction itself we can find out whether the particular instruction belongs to format 3 layout or format 4 layout. In format, if the instruction belongs to format 4 layout, at the prefix a plus sign will be there. It means it is extended format. Extended means format 4. Okay. So this instruction belongs to format 4. Now let us write this instruction in instruction layout format. Opcode 4B, so it has to be written in 6 bits. 4 is 0100, B is 10. Only 2 bits I am writing. Then since it is an format 4 instruction, the value of E should be 1. This comes under simple addressing. If it is a simple addressing means both the value of N and I should be 1 or either 0. So I am writing it as 1. You can write a 0 also. Address. Address is the address field that we have in our instruction itself, that is RD or EC is present in the address 1036. 1036 is represented like this: 1, 0, 3 and 6. Since we have to represent in 20 bits, so I am preceding it with a 0. So this is our address, final address. Now let us write the object code, opcode for our instruction layout. So split it as 4, 4. So 0100 is 4, 1011 is B and 0001 is 1. So final object code is 4B101036. So this is our final object code. So that's all about instruction format, 4 formats: format 1, format 2, format 3 and format 4. Next, addressing modes. So in SIC architecture we have seen about 2 addressing mode depending upon the value of x. If the value of x is equal to 0, it is direct addressing mode, and if the value of x is equal to 1, it is indirect addressing mode. So along with these 2 addressing modes, we are having 3 more addressing modes in our SIC XC architecture, that is base relative addressing mode, program counter addressing mode and indexed addressing mode. So now first let us see about base relative addressing mode. If it is a base relative addressing mode, we have to place B equal to 1 and P equal to 0. Then the target address is calculated by target address B is equal to the value that is present inside the base register plus the displacement that have been mentioned in the instruction itself. Then for program counter, So program counter instruction addressing mode, P equal to 1 and B equal to 0. The target address is calculated by the value that is stored inside the program counter plus displacement. The target address that has been calculated by base relative addressing mode should be in the range of 0 less than or equal to displacement less than or equal to 4095, that is between 0 and 4095, whereas the target address that have been calculated under program counter should be between the value minus 2048 to plus 2047. Next, indexed addressing. For indexed addressing, we have to place x is equal to 1. The target address is calculated as the value that is stored inside the index register plus displacement. Here we won't specify any range and all for the calculation of target address. The indexed addressing will always come along with a base relative or a program counter, so we can take that range. That is, for base relative it should be between 0 to 4095, and for program counter it should be between minus 2048 to plus 2047. So always indexed addressing mode comes along with base relative or program counter addressing mode. Now let us see an example for each of this. Base relative addressing mode. The example instruction is STX length. So the opcode for STX is 13 and the label length is stored in the address 0000. So how we will write this instruction? We will write this instruction as the instruction format, either in format 3 or in format 4. Since plus sign is not in this instruction, so this instruction belongs to format 3 layout. So we will write this instruction in format 3 layout. Opcode is 13, so you have to represent 13 in 6 bits. 1 is 0001 and 3 is 0011. So I am writing only 00. Then simple addressing. For simple addressing, we have to mention both n and I value as 1 and x is equal to 0. Since it is a base relative addressing, B should be 1 and P should be 0. Since it is format 3 instruction, E should be 0. Displacement is nothing but the address of the label length. So the address is 0000, so you have to represent it in 12 bits. 0000, 0000, 0000. So how the target address is calculated if it is a base relative addressing mode? So target address is equal to the value that is present inside the base register plus the displacement field. Let us assume that the value that is present inside the base register is 0011. So how the target address is calculated? That is equal to 0011 plus displacement 0000. So this would be the final target address. Then program counter. Next example is for program counter. The instruction is STL-RETADR. So the opcode for STL is 14 and for RETADR it is stored in the address 02D. This is also comes under format 3 instruction since no plus sign is in the preceding field. So the opcode for STL is 14. Let us write this in instruction layout, format 3 instruction layout. 1 is represented as 0001 and 4 is represented as 0100. Now we have to represent only in 6 bits, so I am leaving the remaining 00. Then it is a simple addressing, so n and I is 11. X value is 0, B value is 0. Program counter addressing, this is an example for program counter. So the value of B is 0 and P is 1. Since it comes under format 3 addressing, the value of E is 0. Displacement is the address 0 to D. 0 is 0000, 2 is 0010 and D is 1101. So how the target address is calculated? Target address is equal to the value that is stored inside the program counter plus displacement. Displacement value is 0 to D. So when we add both, the result will give us the target address. Next, let us see an example for indexed addressing. So indexed addressing STCH buffer, x. So this is the example instruction for indexed addressing. Always indexed addressing can be found out from the instruction itself. So the instruction will contain like this, comma X. So if the instruction contains comma X and it's a fixed field, then this belongs to indexed addressing mode. The opcode for STCH is 54 and the address of the label where buffer is stored is 003. So how we will write in? Format 3 instruction layout. 5 0 1 0 1, 4 is 0 1 0 0. I am leaving the last 0 0. Then since it comes under simple addressing, n and I should be 1. It is indexed addressing, so the x value should be 1. I already told that always indexed addressing comes along with base relative and program counter. Now let us consider that this instruction belongs to base relative addressing. So b equal to 1, p equal to 0. Since it is a format 3 instruction, e equal to 0. Then displacement is nothing but the address of the operand, 003. This is represented like 003. So this is our final opcode for our indexed addressing instruction. Apart from these addressing mode, that is base relative, program counter and indexed addressing, we are having one addressing mode, simple addressing. In simple addressing, target address is taken as location of the operand. All the instruction will comes under simple addressing. If it is a simple addressing, as I told before, the value of n and I should be either 0 or 1. Indexed addressing comes along with base relative and program counter addressing, but it cannot be used with immediate or indirect addressing modes. So this is the one point that you have to remember. Indexed addressing cannot be used with immediate or indirect addressing modes. Then coming to the next hardware feature, instruction set. So in addition to the instruction set that we have seen in our SIC, we are having some other instruction sets, LDB and STB, that is load and store the registers. This is used for loading and storing. And since floating point hardware is available, floating point of arithmetic operations is available in SIC-XC, that is addf, subf, mulf and divf. RMO instruction, register move instruction, is also available in SIC-XC, and SVC, supervisor call instruction. It is also available in our SIC-XC. So this SVC, supervisor call, will generate an input. Supervisor call generate an interrupt that can be used for communication with OS, our operating system. So that's all about instruction sets. Next, input and output. For performing input and output, there are IO channels that can be used to perform input and output while the CPU is executing other instructions. Since there are separate IO channel for performing input and output, the efficiency of the system is very much increased. So the instructions that are used for performing input and output operations are SIO. SIO is start the operation of IO channel, and TIO is test the operation of IO channel, and HIO is halt the operation of IO channel. So these are about input and output. So we have seen all the hardware features that are available in SIC-XC. SIC-XC is an upward compatibility model of SIC. So whatever we have seen in SIC is also present in SIC-XC. Along with that, some extra equipments we have seen. So in our next class, we will see about the next machine architecture, that is CISC machine architecture, complex instructional set computers. Under complex instructional set computers, we are going to see about the hardware features available in two architectures, VAX architecture and PowerPC architecture. So let us see in the next class. Thank you.